Welcome to this deep dive. Today we're looking at the James Webb Space Telescope. You know, the successor to Hubble. And it's probably one of the most ambitious space projects ever.
It really is quite something.
And our aim here is to sort of unpack it all for you, give you the essentials on this incredible observatory without getting too bogged down.
Exactly. We want to get into the vision behind it, the amazing technology, and also the huge global effort that made JWST happen.
Yeah.
So if you've seen those incredible pictures and you're wondering, how did they do that? Why is it so special? Well, you're definitely in the right place.
Perfect. We know you want that knowledge without the overwhelm, so let's just dive right in. What was the big idea behind JWST back in the late 90s when they first dreamed this up?
Well, the core idea, the real driver, was wanting to answer some really big fundamental questions about how the universe started.
Okay.
Scientists were thinking, we need a telescope powerful enough to see the very first galaxies actually forming, to watch stars being born, planetary systems coming together.
Stuff Hubble couldn't quite reach.
Right. The key insight was realizing that to see that far back, billions of years back, you absolutely needed to look in infrared light.
Infrared. Okay, we hear that term a lot with Webb. Why infrared? What's the magic there?
Okay, think about it like this. The universe is expanding, right?
Right.
So the light from those very first, very distant galaxies has been traveling towards us for billions of years. And as it travels through expanding space, the wavelength of that light gets stretched out.
Stretched like a rubber band.
Sort of, yeah. It shifts down the spectrum towards the red end and eventually way out into the infrared part of the spectrum.
Ah, so it's light that started out visible maybe, but it's been stretched so much it's now invisible infrared heat, basically?
Precisely. So if you actually want to see those ancient objects, you need a telescope specifically built to detect infrared. Hubble's amazing, obviously, but it was mainly built for visible and ultraviolet light, not so much this deep infrared.
Okay, that makes sense. So to catch those really faint, stretched out infrared signals from, the dawn of time, you'd need a much bigger mirror to collect more light.
Absolutely, a much bigger mirror. JWST's primary mirror is 6.5 meters across. That's huge.
6.5 meters compared to Hubble.
Hubble's was about 2.4 meters. So Webb's mirror can gather over 6 times more light, which is crucial for seeing those incredibly faint, distant objects.
Wow. Okay.
And here's where the engineering gets really clever. That massive mirror isn't one solid piece. It's actually made of 18 separate hexagonal segments.
Hexagons, like a honeycomb. Why that shape?
It's a really smart way to build a large mirror that, crucially, can be folded up. See, a 6.5-meter mirror is too big to fit into any existing rocket fairing in one piece.
Right, wouldn't fit.
Exactly.
Yeah.
So the hexagonal segments allow it to be folded, almost like origami, really complex origami.
Yeah.
Then once it's in space, it unfolds into one large, near-perfect reflecting surface.
Incredible. And what are those segments made of? I remember reading it was something pretty special.
Yeah, they're made of beryllium.
Beryllium.
It's this amazing metal. It's incredibly light, which is super important for launching anything into space. You want to keep the mass down. But it's also really strong and critically very stable at extremely low temperatures.
Ah, the cold thing again. We'll get to that.
We will. That stability is key for keeping the mirror's shape perfect when it's operating at, hundreds of degrees below freezing.
And they're coated in gold, right? Is that just for looks?
No, not just for looks, although it does look amazing. Each segment has this ultra-thin coating of gold.
Why gold?
Because gold is exceptionally good at reflecting infrared light, better than almost anything else. So that thin gold layer maximizes the amount of faint infrared signal the telescope actually captures and sends to the instruments.
So you've got this huge segmented gold-coated beryllium mirror that folds up. The engineering challenge just seems immense.
It was mind-boggling, designing it, building it, testing it, making sure it could survive launch, and then deploy perfectly millions of kilometers from Earth.
Yeah.
Yeah, a huge challenge.
And speaking of challenges, you mentioned the cold. Keeping this thing freezing cold is essential for infrared. That's where the giant sun shield comes in, isn't it?
Absolutely critical. The sun shield is maybe just as impressive an engineering feat as the mirror in its own way.
Why so crucial?
Because to detect those incredibly faint infrared signals from distant galaxies, the telescope itself, its mirrors and instruments, have to be unbelievably cold. We're talking around minus 220 degrees Celsius, or about 40 Kelvin if you prefer.
Minus 220 C. Wow.
Yeah. Any heat from the telescope itself, or any stray heat and light from the sun, or even Earth and the moon, would just completely swamp the faint signals it's trying to detect. It'd be like trying to spot a candle flame next to a searchlight.
Okay, so the sun shield blocks the searchlight.
Exactly. It's this enormous 5-layer shield. Each layer is made of a special plastic called Captain, coated with aluminum and silicon. And when it's fully deployed, it's roughly the size of a tennis court.
A tennis court. In space.
Yep, blocking the sun.
Why 5 layers? Wouldn't one thick layer do?
Good question. The multi-layer design is incredibly effective. Each layer is very thin, thinner than a human hair, actually, and they're separated by a vacuum gap.
Okay.
So the first layer facing the sun gets hot, but it reflects a lot of heat away. The gap insulates, and the second layer is much cooler, reflects more heat, and so on, down through the 5 layers.
Like a super insulating stack.
Precisely. Each layer radiates heat out into space on the sides, and by the time you get to the 5th layer on the cold telescope side, it's incredibly cold. It's a very efficient passive cooling system.
And just like the mirror, this giant, delicate, tennis court-sized thing also had to be folded up for launch.
You got it. Folded very carefully, very compactly, and then once in space, it had to execute this incredibly complex sequence of unfolding, separating the layers, and tensioning them all perfectly. Another huge point of anxiety during deployment.
The scale of this project, it's just hard to comprehend sometimes. And this wasn't just NASA working alone, was it? This was a global effort.
Oh, absolutely. JWST is a fantastic example of international collaboration. NASA led the project, definitely. But the European Space Agency, ESA, and the Canadian Space Agency, CSA, were absolutely vital partners.
What were their main contributions?
Well, ESA's contribution was huge. They provided the Ariane 5 rocket for the launch, which was, critical. They also contributed key parts of some instruments.
And Canada.
CSA provided the crucial fine guidance sensor, which is what allows the telescope to point so incredibly precisely and stay locked onto targets.
Right.
They also contributed another science instrument, NARS. So, yeah, truly a partnership.
And then there are the companies that actually built the hardware.
Right. You had major aerospace companies involved.
Yeah.
Northrop Grumman was the prime contractor. They were responsible for the overall design, building the spacecraft bus, the sun shield, and integrating everything together, plus testing. And Ball Aerospace built those amazing beryllium mirror segments we talked about, very specialized work. And then, of course, teams from NASA centers, universities, and institutions across the U.S., Europe, and Canada built the scientific instruments.
Let's touch on those instruments quickly. The things actually doing the science, there are 4 main ones.
That's right, 4 main instruments. There's NIRCam, the near-infrared camera. That's kind of the workhorse imager, the one taking many of those spectacular pictures, really designed to see the first stars and galaxies.
Okay, then ICAM.
Then NIR-SPEC, the near-infrared spectrograph. This one is amazing. It breaks down the light from objects into its constituent colors, like a prism. That tells you about their chemical makeup, their temperature, how fast they're moving, their distance. And NIR-SPEC can observe hundreds of objects at once.
Wow, efficient.
Very. Then there's MARI, the mid-infrared instrument. This one sees even longer infrared wavelengths, which is great for looking through dust clouds to see stars being born inside, and for studying the cooler objects in the universe, like planet-forming disks and even objects in our outer solar system. MARI was a big European contribution, actually, a partnership between Europe and NASA JPL.
Got it. And the last one?
The last one is FGS-A. FGS is the fine guidance sensor from Canada that we mentioned for pointing. NIRI is the near-infrared imager and slitless spectrograph, also from Canada, which does its own science, particularly good for studying exoplanet atmospheres.
Exoplanet atmospheres. Amazing. And each of these incredibly complex instruments had to be built, tested, and then somehow integrated perfectly to work together in deep space conditions.
Exactly. The level of meticulous integration and testing required was just phenomenal. Everything had to work perfectly first time.
Now, a project this complex, this ambitious, it wasn't exactly smooth sailing all the way, was it? I seem to recall hearing about delays and budget issues over the years.
Oh, absolutely.
Yeah.
That's definitely part of the story. JWST faced, well, quite a few years of delays and significant budget increases compared to the initial estimates.
What caused that? Just the sheer difficulty?
Largely, yes. The technology was genuinely groundbreaking. Things like the segmented mirror, the deployable sun shield, the ultra-sensitive detectors, they pushed the envelope. Developing them, testing them, ensuring they would work reliably in space.
Yeah.
It just took longer and cost more than originally anticipated. There were technical hurdles, integration challenges. It's a very complex machine.
Did those delays end up having any maybe unexpected upsides, like more time for testing?
You could definitely argue that. While frustrating at the time, the extended schedule certainly allowed for incredibly thorough testing and refinement. I mean, with something this complex where you can't go and fix it if something goes wrong.
Yeah, no astronauts flying out to L2 for repairs.
Exactly. That extra time spent on ground testing, ironing out potential problems, was probably invaluable. It likely played a big role in how smoothly the deployment and commissioning actually went in the end. That final phase of assembly and testing at Northrop Grumman in California was exhaustive.
Okay, so after all the building and testing, it was finally ready. How do you even get something that big and delicate to the launch site in French Guiana? You can't just pop it on a plane, can you?
Huh. No, definitely not. It was a major logistical operation. The telescope, all folded up, was carefully placed inside a specially built, environmentally controlled container, like a huge high-tech shipping box called TTARS.
Stitar.
Space Telescope Transporter for Air, Road, and Sea. This massive container protected it from humidity, contamination, shocks, everything. Then it was transported very carefully by ship from California, through the Panama Canal, all the way to the port near Kourou in French Guiana.
An epic journey even before it left Earth.
Absolutely. Meticulously planned.
And then launch day, Christmas Day 2021. Must have been an incredibly tense moment for thousands of people worldwide.
Oh, without a doubt. A hugely anticipated and, nail-biting moment. But the launch itself on the ESA-provided Ariane 5 rocket was just flawless. Perfect.
A great Christmas present for space fans.
It really was. The rocket performed beautifully, placing Webb precisely onto its trajectory out towards its destination, which wasn't Earth orbit, but a special point much further away.
Right, the L2 point, the second Lagrange point. Why send it way out there, 1.5 million kilometers away?
L2 is a really neat spot in space. It's a kind of gravitational balance point, about 1.5 million kilometers from Earth, directly away from the sun.
Okay.
So if you put a spacecraft there, the combined gravity of the sun and Earth holds it in roughly the same position relative to us as we orbit the sun. It sort of orbits the sun with the Earth.
Why is that good for Webb?
Two main reasons. One, it's gravitationally stable, meaning the telescope doesn't need to use much fuel to stay there. It can just hover relative to Earth. That helps extend its mission lifetime.
Saves gas, basically.
Exactly. And second, and crucially for an infrared telescope, from L2, the sun, Earth, and moon are always basically in the same direction in the sky.
Ah, so the sunshield can always face them.
Precisely. The sunshield can constantly face the sun, Earth, and moon, keeping the telescope and its instruments permanently shaded and incredibly cold, which is exactly what you need for those sensitive infrared observations. It simplifies the thermal design enormously.
Clever. Okay, so it launched perfectly heading to L2, but the journey wasn't the end of the drama. That whole deployment sequence in space, that sounded incredibly risky.
Absolutely. The month after launch was probably the most complex sequence of deployments ever attempted for a space mission. Hundreds and hundreds of individual steps had to happen perfectly.
Hundreds? What kinds of things?
Oh, deploying the solar array, the communications antenna, then the massive multi-step unfolding and tensioning of the 5-layer sunshield. That alone took about a week. Then deploying the secondary mirror on its long boom, and finally unfolding the 2-side wings of the primary mirror segments and latching them into place.
It sounds like a recipe for disaster. So many single points of failure.
Over 300, actually. Over 300 single points of failure, meaning if any one of those critical steps didn't work exactly right, it could have potentially doomed the entire mission or severely compromised it.
300? That's unbelievable pressure on the engineering and the mission control team.
Immense pressure. But incredibly, every single step worked flawlessly. It was just an astonishing display of engineering and planning. The precision was incredible.
I remember following the sunshield deployment updates day by day. That seemed particularly fiddly.
It really was. Getting those 5 enormous, extremely thin layers unfolded, separated, and pulled perfectly taut without snagging or tearing. I mean, it was happening autonomously, 1.5 million kilometers away. The mission team could only watch the telemetry, but it worked perfectly. An absolute triumph.
So deployment complete, telescope in place at L2. Was it ready to start taking pictures then?
Not quite yet. After the major deployments, there was still a long commissioning phase lasting several months.
What did that involve?
First, the telescope had to cool down to its operating temperature, shielded behind the sunshield. Then came the incredibly painstaking process of aligning the 18 primary mirror segments.
Aligning them. How precise did that need to be?
Unbelievably precise. Each of the 18 segments had tiny motors on the back, allowing them to be tilted and adjusted. They had to align them so accurately, we're talking adjustments on the scale of nanometers, billions of a meter, that all 18 segments acted together as one single, perfect 6.5-meter mirror.
Manometer precision from millions of kilometers away.
Yep. They used a star as a reference point and iteratively adjusted each segment until the images from all 18 lined up perfectly into one sharp focus. Then they had to calibrate all 4 science instruments, making sure they were working exactly as expected.
Okay, so months of fine-tuning, and then finally, the big reveal, July 12th, 2022. Those first images were released to the world.
Yes, that was the moment everyone had been waiting for years, decades even. And the images, they were just breathtaking, absolutely stunning.
Which one stood out for you initially?
Oh, all of them were incredible. That view of the Carina Nebula, the cosmic cliffs, showed star birth with unbelievable clarity. Stephan's quintet, the galaxy cluster, revealed details of galactic interactions we'd never seen before. The Southern Ring Nebula, a dying star. Just beautiful and scientifically rich.
And the deep field image.
Wow, Webb's first deep field. That one was just mind-blowing, pointing at a tiny patch of sky, seemingly empty, and revealing thousands of galaxies stretching back over 13 billion years. Seeing some of the faintest, most distant galaxies ever observed right there in that first image. It was an immediate demonstration of Webb's power.
It really felt like humanity had suddenly got new eyes on the universe. The sharpness, the depth, the detail. It was unlike anything Hubble had shown us in those wavelengths.
Exactly. It wasn't just about prettier pictures, though they are gorgeous. It was the sheer amount of new information, the level of detail in the infrared that was suddenly accessible. We started seeing structures within distant galaxies, peering through dust clouds, analyzing the light from exoplanets, things that were simply impossible before.
It's already changing astronomy, isn't it?
Fundamentally, it's driving new questions, confirming some theories, challenging others. It's providing data that will keep astronomers busy for decades.
So when you look back at the whole story, the initial dream, the decades of work, the technological hurdles, the international teamwork, the delays, the nail-biting launch and deployment, and now these incredible results. What's the big takeaway for you? What does JWST really represent?
For me, it really represents a couple of things. First, it's a testament to human ingenuity and our sheer persistence in trying to understand the universe, the audacity of even trying to build something this complex.
Yeah.
Second, it's a powerful symbol of what international collaboration can achieve, pulling together expertise and resources from NASA, CSA, and countless researchers and engineers worldwide. It shows what we can do when we work together on big, ambitious goals.
It really does feel like a milestone achievement, not just for astronomy, but for, human endeavor generally.
Absolutely.
Yeah.
It pushed the boundaries of technology in so many areas: materials, science, optics, cryogenics, deployment mechanisms. The list goes on. It's an incredible feat of engineering.
And it's really just getting started, isn't it? Its mission is planned for many years.
Oh, yes. Decades, hopefully.
Yeah.
It's performing extremely well. Fuel reserves look good thanks to the precise launch. It has the potential to be rewriting textbooks and revolutionizing our cosmic perspective for a long, long time.
It's truly a legacy of innovation.
It absolutely is. A legacy that will hopefully inspire the next generation of scientists and engineers.
So as we wrap up this deep dive on the James Webb Space Telescope, here's something for you to think about. This incredible, intricate machine, built by people collaborating across the globe, allows us to literally look back towards the beginning of time to see the universe taking shape.
Yeah, it's pretty profound.
So, consider this. How does knowing we can do that we can build tools to witness cosmic dawn, maybe change how you think about our own small place in this enormous ancient universe? And what discoveries, still unimagined today, might this telescope reveal in the coming years that could completely reshape our understanding of existence itself?